So now that we know what makes something an acid or a base, let's look at how we can calculate pH, pOH, and what those numbers actually tell us about our solutions. So let's start by looking at what is pH. pH stands for potential hydrogen. So it's a measure of the amount of the hydrogen ion concentration in solution. So our pH tells us how much hydrogen ion is in solution, what's the concentration of it. And it determines whether the solution is acidic or basic. So we have what's called a pH scale. Now we've probably seen this before. It's a scale that ranges from 0 to 14. 7 in the middle is neutral. Our strong acids have a pH towards the 0 end of our scale, and our strong bases have a pH towards the 14 end of our scale, the high end. Weak acids tend to have a pH closer towards 7, closer towards neutral. And weak bases also have a pH closer towards neutral, but on the basic side. So that's what our pH scale tells us, how acidic or basic is our solution. So now let's look at how we calculate this. So the formulas are pretty straightforward, and we're going to start with the acids, because those are the ones that we can directly measure with pH. And to calculate pH, it's the negative log base 10, so it's a 10 base logarithm of our hydrogen ion concentration. So in a question, I would say you have a concentration of whatever 1.0 times 10 to the negative fourth hydrogen ions. What's the pH? Well, it's just negative log of whatever that concentration is. A logarithm really just takes really big or really small numbers and turns them into integers. It's a scaling piece. So all we're doing is scaling our concentrations to much more manageable numbers. To determine the hydrogen ion concentration, we just have to do the antilog, or 10 to the negative pH. So the antilog of a logarithm is 10 to an exponent, and in this case we're going to do negative pH because that will get us the inverse of our pH equation. For bases, we tend to look at pOH, or the potential hydroxide ion concentration, and these equations are very, very similar. So again, to get pOH, it's negative log of your hydroxide concentration. So very similar to hydrogen, but instead of using the hydrogen ion, we're using the hydroxide ion. That'll get us pOH. And then same thing to determine our hydroxide ion concentration. It's the antilog to the negative pOH. So it's the same as our hydrogen ion, but instead of negative pH, we use negative pOH. So that's how we can get back and forth between our ion concentrations and our pH or our pOH. Now there's another really easy thing that we can use to do these calculations. pH plus pOH equals 14. So if you know the pH, you can calculate the pOH, and if you know the pOH, you can calculate the pH, because if you add the two together, they always equal 14. So let's put these equations into practice. We're going to walk through 5 different examples to look at the different types of calculations that you might see. Our first example says calculate the pH of 0.045 molar hydrobromic acid, or HBr. Now, HBr is a strong acid, so we know that it is going to completely dissociate. That means that our concentration of our HBr is equal to the concentration of our hydrogen ion. That's because it is a strong acid. I won't ever give you problems where you're not going to have a strong acid if it's something written like this, because we don't know how to calculate pH from a weak acid, and that's not something we're going to focus on in this class. So we're going to focus on the strong acids. So that means that our concentration of HBr is 0.045, which means our hydrogen ion concentration is 0.045 molar. And my question asked me to calculate pH, so pH is equal to the negative log of 0.045 molar, which means my pH is 2.35. That's all it is. So I type this into my calculator, negative log 0.045, and my calculator would tell me that the answer is 2.35. And there aren't units on pH, so that's our final answer. Our second example says, what is the pH of 1.2 times negative to the third molar NaOH? So sodium hydroxide is a base, but we can still calculate the pH of a base because it's just telling us how much hydrogen ion concentration there is. So if we have a strong base, that means, look at my notes. Our sodium hydroxide concentration is equal to our hydroxide concentration because sodium hydroxide is a strong base. So that means that our hydroxide ion concentration is equal to 1.2 times 10 to the negative third molar. Now, we can't go directly from hydroxide to pH, but we can go from hydroxide to pOH and then to pH. So let's do that. So our pOH would be our negative log of 1.2 times 10 to the negative third. When you type that into your calculator, you get that your pOH is equal to 2.92. So that's step one. Step two, we know that pH plus pOH equals 14. So pH will be equal to 14 minus our pOH. We know our pOH, we calculated that in step one. So now our pH will be 14 minus 2.92, which leaves us with our pH of 11.1, which is what we would expect. We're looking at a base. It has a fairly high concentration of hydroxide ion, which means it's going to have a pH that's closer to the 14 side. Let's look at our next example. Our example 3 says, what is the pOH of a solution with a pH of 8.4? So if we're going to get from pH to pOH, we need to know that pH plus pOH equals 14, which means our pOH would be 14 minus our pH. We know our pH, that was given to us in the problem. So our pOH equals 14 minus 8.4, which leaves us with a pOH of 5.6. So really we're just using the same equations and manipulating them in different ways to find the answers we're looking for. Okay, we have two more examples. Example 4 says, what is the hydrogen ion concentration of a solution with a pH of 11.4? Now remember, our hydrogen ion concentration is equal to the antilog, or 10, to the negative pH. So our hydrogen ion concentration would be equal to 10 to negative 11.4. When you type that into your calculator, 10 to the negative 11.4, so either the caret or if you hit second log, it will do the same thing. Leaves us with our hydrogen ion concentration is equal to 3.98 times 10 to the negative 12 molar. Now, there are units on this because it's a concentration, and so the units are going to be molarity. So you have to make sure that you put the molar on the end because it is a concentration, and concentrations do have units. So if you have a pH of 11.4, you have an extremely low hydrogen ion concentration. That makes sense. pH of 11.4 is fairly basic, which means you're not going to have a whole lot of hydrogen ion. Okay, let's look at our last example. Example 5 says, what is the hydroxide ion concentration of a solution with a pH of 4.9? Now again, we can't go straight from pH to our concentration of hydroxide, but we can go from pH to pOH to hydroxide. So step 1 is going to go from pH to pOH. Step 2 will go from pOH to our concentration of our ion. So for step 1, we know that pH plus pOH equals 14. That would mean pOH would be equal to 14 minus pH. Plug our numbers in because we know our pH. pH is up here, it's 4.9. So our pOH is equal to 9.1. Okay, so now we're at pOH. To get to our hydroxide ion concentration, we know that that concentration is equal to the antilog, or 10, to the negative pOH. Now we know our pOH that's down here, so we're going to plug our numbers in. 10 to the negative 9.1. And then if we type that into our calculator, we get that our hydroxide concentration is equal to 7.94 times 10 to the negative 10th molar. And again, we need units on it because it's a concentration, therefore we have to make sure that we put our molar units on at the end.